Hello, everyone, and welcome to today's webinar hosted by SPIROL, where we will talk about coiled spring pins and specifically how light duty can benefit your applications. My name is Max, and I am the product manager responsible for spring pins in SPIROL, and I will be monitoring the webinar today. This will be an interactive session where you can submit your questions on the topic, and we will answer them later after the presentation. To submit your questions, please enter them into the Q&A sections of the chat. Now, I'm pleased to welcome and introduce today's expert presenter, Adolf Vasilik. Adolf is SPIROL's application engineering supervisor in his third year with the company and is a great resource for our customers as well as our internal team members.
Thanks, Max, for the introduction. My name is Adolf. I have a master's degree in mechanical engineering, and my background is full of machine tool design, product development, and academic research. As an applications engineer in SPIROL, I thoroughly enjoyed the variety of customer application challenges that I helped to resolve, as well as the exposure to just so many different industries. So thank you all for attending, and let's get into the presentation. As the webinar's name suggests, we will be focusing on light-duty pins and their benefits today. To set the ground, we'll cover some general benefits of spring pins that apply to all of their kinds, then how coiled pins differ from other types and in which way they can be beneficial. And as the coiled pin comes in three different duties, we'll cover and explore them and explain the differences between them, as well as the typical guidelines of their selection. After this, we'll focus strictly on the light duty and explore the individual benefits that it has over the other coiled pin duties. These benefits can be taken advantage of in a variety of different specific applications, which will be the next topic. Then conclusions will be drawn and key takeaways introduced for you to remember going forward and thinking about in new designs.
Now, before we get into the main portion of the webinar, I would like to first introduce our company and what we do for those who are not completely familiar with us. SPIROL is a global manufacturer and supplier of engineered components used for fastening, joining, and assembly. We have 12 major product lines, each one designed to improve product quality, simplify the assembly process, and/or reduce the overall cost of the assembly. We are the only company who designs and manufactures both our engineered fasteners and the installation equipment of those fasteners. Our focus, though, is not just supplying high-quality product, but it is in working with our customers as early as possible in the design stage to help them choose not only the fastener, but also to make the critical recommendations between our product and their components so that when the assembly goes together, it stays together for the intended life of the assembly.
Right, so let's get into the spring pins. They are a mechanical fastener used in a variety of applications. The primary method of retention here is by radial tension, which is a result from their interference fit with the host component. As opposed to other interference fit fasteners, the key difference here is that the spring pin is designed to be the compliant element in the joint and therefore protect the host component from incurring damage either from installation or further loads, shocks, or vibrations that the assembly might incur over its life. The amount of flexibility also enables larger hole tolerances, resulting in lower manufacturing costs, as the holes typically do not require reaming, which would be an extra step, and are completely fine just drilled, stamped, or as cast. A spring pin, however, as I've just described, is a very general term, and many types of fasteners would satisfy these definitions. All of these pins, bushings, or tension sleeves would classify as spring pins. Two of them, however, are the most prevalent: the slotted pin and the coiled pin. The slotted pin is distinguished by its longitudinal slot and a C-shaped cross-section, while the coiled pin is characterized by its 2 1/4 wraps of material. We always promote the coiled pin as the more flexible option. But why exactly is that? Well, there are two reasons. First of all, there is no slot, as is in the slotted pin, because when that closes, the pin is essentially a solid tube and cannot move forward. The coil pin can just coil further to absorb whatever load as seen in this animation. The second reason is a fundamental principle of flexibility and the same reason why cables are more flexible than wires. Rather than having a solid cross-section, it is split into finer layers. Bend a wire over and over again, and it breaks in fatigue. Bend a cable over and over again, and nothing will happen. As I've already mentioned, the coil pin is normally available in 3 different duties: light, standard, and heavy. The difference between them is that they use different raw material strip thicknesses while maintaining the same 2¼ coils cross-section. The raw material thickness determines how much material there is and therefore the pin's strength and flexibility. The duty selection is therefore driven by the application's requirements for these 2 factors. As a company that invented the coil pin, we can also customize the duty and cross-section to suit a specific application. One of the more frequent versions that we make is the so-called extra light duty, which uses the same material thickness as the light duty, but only has 1½ coil cross-section for even more flexibility. As the different duties have a different level of flexibility and therefore radial tension, host materials have a limit to the duty that can be used in them. Plastics, ceramics, soft die-cast components are normally limited to light duty. Then mild steels or other non-ferrous metals such as aluminum, brass, or copper permit the use of standard duty, while heavy duty is reserved for hardened steels, applications with a substantial boss diameter, or severe shock and vibration environments, or due to spatial constraints where a larger pin cannot be used. We always want to avoid using heavy-duty pins for soft materials or ceramics because the amount of radial tension would damage or destroy the host component. But can we use a light-duty pin in a hardened steel application? Well, absolutely. There is nothing preventing you from using a lighter-duty pin in a heavier-duty host material, as long as the strength requirements of the application are met, of course. Doing this actually brings a lot of benefits that we'll cover just in a minute. Light duty is a lot of times incorrectly associated with low strength, probably due to its name. I guess we could have done a better job naming it. In this table, we see a double shear strength comparison between a low carbon steel solid groove pin and a high carbon steel light duty coil pin. We're talking 2.3 kilonewtons versus 3.5 kilonewtons in a 2.5 millimeter nominal size, or 23 kilonewtons versus 31.2 kilonewtons in an 8 millimeter nominal size. Sure, the light duty has a slight disadvantage, but we're talking in kilonewtons here. A 6 millimeter light duty pin with its 13 kilonewtons of double shear strength is strong enough to hold a small passenger car. In most applications, the strength is not the primary driver of pin selection because it is often difficult to determine the actual loads in the application. And the pins are usually sized and selected based on gut feeling and/or proportions to the assembly. This can sometimes lead to an overkill solution in terms of strength. So whenever the application permits, utilizing a light-duty coil pin in the design can bring a host of benefits, both technical and commercial. The first one being a reduction in insertion force. Light duty has the lowest insertion force out of all the duties, roughly half that of a standard duty pin and approximately quarter that of a heavy duty pin. Looking at some, sorry, I skipped there, right. Looking at some approximate values for a 4 millimeter pin here, you can see that we would expect around 5.1 kilonewtons of insertion force for every 25 millimeters of engagement of the pin length for heavy duty, which is a lot. When we move to standard duty, we see an improvement at approximately half the force at 2,450 newtons, and moving to light duty, we're seeing half that again at just 1,200 newtons. Now, these are just orientational values, as the actual forces may vary a lot depending on other factors, but it gives a perspective to how much easier it is to install a light duty pin. Now, this advantage goes beyond simply comparing the duties within the same diameter. If your objective is to reach a certain shear strength while having the lowest insertion force, a bigger light-duty pin will always have a lower insertion force than a smaller equivalent strength standard or heavy-duty pin. A lower installation force is beneficial to the overall ergonomics of a manual assembly process, but also helps to prevent repetitive strain injuries. as well as making any mechanization or automation of the process just so much easier. Now, another benefit is an enhanced protection of the host component. Of all pinning solutions, the light-duty coil pin stresses the host component the least thanks to its flexibility. This can be visualized in an experiment. We have installed different pins into clear acrylic. Now, this material has a pretty cool property that it refracts light under stress, and it can be visualized fairly easily, meaning that the stress in the material can be seen by a naked eye. As you can see here, there's a lot of rainbow rings over the solid pin installation, but evenly spaced out. When we move into a spring pin, the amount of rainbow effects is a little bit lower, but you can also notice a typical trilobular contact or three-point contact with a slotted pin, where the pin engages the material directly opposite the slot and then 120 degrees apart. Moving into the coil pins, we can see the amount of rainbowing being slightly lower again and having multiple contact points around the perimeter of the pin, again improving the engagement. Moving into standard duty pin, we can see the amount of stress being lower yet again, and again evenly spaced out, with the light duty pin essentially bearing no stress into the plastic and being the most evenly spaced. This behavior of the light duty coil pin means that it lowers the possibility to damage the host material. Even when the pin shears, when its strength is exceeded, the host material remains untouched, which promotes further serviceability and longevity of the application. It's always so much cheaper to replace just the pin compared to when you have to rework the parts or source a new one, right?
Absolutely.
And finally, the most attractive benefit is, as usual, lower cost. Now, the lower cost benefit has many different components making it up, because we're talking about the overall cost of assembly. The first one being the most obvious, it's the lower component piece price. Light duty uses less raw material and therefore saves approximately 10% of the cost compared to a standard duty coil pin. The second component that contributes to an overall lower assembly cost is that the light duty coil pin is able to accommodate the widest range of hole tolerances and therefore economizing the whole manufacturing process. Another component is the installation equipment itself, which is typically a one-time expenditure, but its capital cost does impact the overall project costing. By using a light-duty coil pin, the machine would not have to be as powerful because of the lower installation force and therefore more economical. As an example here, it could be that by utilizing light-duty pin instead of a standard or heavy-duty, a SPIROL Model PR pin installation machine could be used instead of the more expensive heavy-duty Model CR and achieving approximately a 30% cost saving. All of this combined together is what makes the solution unique, which is best demonstrated by replacing a solid precision ground dowel used for alignment with a light-duty coil pin. The part price savings can be to a tune of 80%, as the grinding operation on the dowels makes them very expensive. Hole preparation costs will be lowered because no reaming operation is required, which is a saving in manufacturing time as well as tooling. And lastly, the installation equipment. Pressing in the solid dowels takes a huge amount of force, making the installation equipment, well, probably an order of magnitude more expensive, and likely requiring a hydraulic press instead of a more economical pneumatic machine. And as a cherry on top, the light-duty coil pin is also lighter, which introduces an additional benefit to weight-conscious industries such as aerospace. So let's put these features and benefits into practice and take a look at some example applications where light-duty is oftentimes the most optimal solution. Starting with alignment applications, which is something that I've already mentioned a couple times during this webinar. By alignment applications, we mean using a fastener to provide precise alignment, location, or indexing during the assembly process of two or more components, while not bearing any direct load or shear forces. Typically, you'll see these applications all over the engine compartment of your car. For example, to align the water pump to the block or other auxiliary modules to be mounted onto a larger body. In the picture here, we have another classic application, a solenoid valve hydraulic manifold off of a heavy-duty truck automatic transmission. When aligning this assembly to the transmission body, you have the following options: a precision ground solid dowel, a cold form dowel, a spring dowel, and a coil pin. As I have already mentioned, using the solid dowels or pins requires very tight tolerance control, and the fasteners are typically more costly. Spring dowels and coil pins, on the other hand, are a lower cost component. Plus, they have the benefit of easier, lower force assembly and permit wider hole tolerances. The light duty accentuates all of these benefits. Now, deciding between a spring dowel and a light duty coil pin is primarily driven by the size of the application, because the fasteners have different size ranges and availabilities. If you are unsure which is the right product for your application, do not hesitate to contact SPIROL for a consultation, because we make both of them. Another very typical application are hinges or articulating joints. For all hand-operated mechanisms and hinges that do not bear shear forces when actuated, the light-duty coil pin is the most universal solution. It allows for adoption of both a free fit and a friction fit hinge to suit all needs, like a 12-volt charger socket in a car, a door handle, a circular saw, articulating hinge. All of these don't really require high-strength fastening, but are mostly judged by how they feel in operation. And thanks to its flexibility, light duty again allows for an easy adoption of a friction fit hinge that holds its position, as well as a regular free fit hinge that can be in some cases combined with a torsional spring, such as is the case with the car door handle here, to provide some forced feedback. The light duty's advantage is that its high flexibility does not damage plastics, which is where we see them used most frequently. Other stronger and less flexible pins could potentially damage the plastic, and the additional strength is of no benefit in the application, because typically the metallic fastener is much stronger than the plastic host. So in situations when something breaks, it's typically not the metallic thing in the assembly. A special subset of applications are cosmetic case hinges. We have a specially designed application-specific product that serves this market, and that will be our Series 550 cosmetic pin. This is actually an extra light duty pin, which is tailored to be used in the small cosmetic compacts as a friction fit hinge component. The feeling of the hinge is extremely important in the cosmetic industry, and a so-called flopper is completely unacceptable. The SPIROL pin is a unique product in the market that provides the desired functionality and has become the industry standard solution over the years. The last example is a general fastening use case of pins. While pinning in general represents the most economical fastening method, take an example of this oil dipstick. What are your options to secure the blade to the body? You can overmold the blade, you can glue it in, weld it in ultrasonically, use a self-tapping screw, or other methods, but all of them pale in comparison to the productivity, ease of automation, and assembly cost of using a simple cross pin. When you have an application that doesn't bear any load, a light-duty coil pin will again represent the most optimal solution thanks to all the benefits that we have gone over. It also allows you to fasten multiple components of various materials together: plastics, metals, ceramics. These could be incompatible with each other with other fastening methods. Because of the general nature of this concept, there is such a large variety of applications. I think all of you could think of at least one product or use case where this could be applicable. So that was an in-depth analysis on how light-duty coil pins can benefit your products. For anyone that joined in later, or for someone who's just looking at the key takeaways to remember from today's webinar, those would be: first, a light-duty coil pin is the most appropriate spring pin product for plastic applications because it does not damage the host component. If you are designing a plastic component which would use a spring pin for one of its traditional applications, start with the light duty. Second, no matter the host material, if you are working on alignment, hinge, or fastening application that is not load-bearing, consider a light-duty coil pin in all materials. Third, when a light-duty coil pin can be used, it represents cost savings to the overall assembly from the component as well as process perspective. And fourth, it makes automatic installation more attainable and manual installation less painful thanks to its lower insertion force. And keep in mind that SPIROL is always here to support you in your design efforts, so please get in touch with us to consult your design choices and let us help you design the most optimal solution. This is a great example that will just illustrate how the light-duty pin can benefit a specific application. What you're seeing is an industrial hydraulic brake treadle, where the pedal is connected to the base in 2 points, the main articulating joint and the push rod. Both connections were originally made with a solid pin, and the pushrod pin used circlips to prevent the pin from falling out because it was free fit all the way through all components. The problem with the solid pins is that they're extremely expensive, as we have said, plus there is an additional cost in the circlips themselves. The actual load on the pin from the operator pressing on the pedal is much lower than the tens of kilonewtons of the pin's actual strength. So the change to a light duty here is absolutely permissible here. And by doing so, the customer was actually able to save 73% on the pin price. Let's just let that sink in. That's not only the benefit of, that's not the only savings though. Because the coil pin is self-retaining, there is no need to use the circlips, which were an additional cost, and a line on the bill of materials for purchasing. There is also a further saving in the assembly process as well. The circlips take a very long time to install on the pin and are extremely finicky. I'm sure if any of you put a circlip on a pin before in your life, you can probably relate. It's really not something you want to do in scale production. It's very hard to automate. And so not having this as the part of the assembly process dramatically decreases the assembly time and therefore cost. And not only that, the new process is much more suitable for automation should the production scale even more. And lastly, the perceived quality of the product was also improved because the coil pin is tight fit in the aluminum brake pedal and doesn't rattle when subjected to vibrations. This was not the case with the free fit solid pin, which was able to move axially, limited by the circlips, but also had a radial clearance to achieve the free fit. And therefore, if this was installed on a forklift and you're driving around, things can rattle. Mm-hmm. And so if you want to read more applications such as this one, study some of our in-depth technical white papers, or learn more about pins in general, I encourage you to visit SPIROL.com and wander around our resources section.
While there, you can also have 3D models of our products available from the website. You can download and insert directly into the model of your assembly.
If you're working on a new design or new project, involve us as early as possible. We will conduct a no-obligation comprehensive evaluation of your application and then provide you with a detailed engineering report, complete with samples for testing and approval. All of this free of charge.
All right, folks, we've received a couple questions here throughout the presentation that we'll be addressing. For those of you that haven't been able to submit, now would be the time to do so, and we'll start addressing them as they come up. And if we do not get to your questions during the live session of the webinar, we will email you the answer to your question shortly after the webinar concludes.
So we have the first question: are they available in stainless steel? And the answer to that would be yes, and yes. We actually have two kinds of stainless steels. We supply in nickel austenitic stainless steel and martensitic chrome stainless steel. These two different stainless steels are different in that the austenitic cannot be heat treated and therefore work hardens, but it's also incredibly corrosion resistant and works really well in chemical environments. Mm-hmm. The martensitic chrome stainless steel is heat treated. It is generally still very good, has very good corrosion resistance in atmospheric environments. And its benefit, because of the heat treat, is that it's much stronger. And we've actually found that in dynamic applications, it is able to last much longer before it fatigues and cracks. So these are the two available stainless steel options. And obviously, the standard material, as for all spring pins, is also high carbon steel for environments which do not really have requirements for corrosion protection.
Great question. Thank you for that.
Now, I could actually expand on this a little bit more because some people choose zinc plating as a form of corrosion protection, but this is not something that we would recommend for coil pins, as the zinc plating doesn't really get inside in the coils as much, and therefore the pins could be of risk of corrosion, let's say from the inside out.
Yes.
And we generally recommend zinc plating only in environments where the zinc is needed for its galvanic properties.
That's correct.
To protect the other components from being anodic and corroding away.
Okay, so we have another one come in here. Another good question. What is the maximum permissible centerline tolerance for alignment applications?
That's a very good question. So when we are aligning multiple components together, typically we need more than one fastener to align it properly. And the centerline tolerance is very important because, for example, with solid dowels, the more imprecise the location is, that increases your installation forces, or maybe that even prevents the actual assembly of the product. With coil pins, because they're more flexible, we can allow that centerline tolerance to not be as precise. Personally, my rule of thumb is to get the chamfer diameter of the coil pin, subtract that from the nominal hole, and that would be my centerline tolerance. Coil pins typically start with a chamfer diameter which is at least 0.1 millimeters smaller than the nominal, and therefore 0.1 millimeters would be that centerline tolerance, generally speaking.
Excellent. Thank you for that. Another question did come in for us. In application where both ends are held, which version of these pins have the best fatigue property when there are micro motion vibration in the torsion?
So, okay, let's imagine we have the pin held from two sides, and then there's another component maybe in the middle, and there are micro motions, vibrations in torsion of that component. Now, for that, we would need to know the magnitude of those vibrations, of the forces that come to it, and then, of course, the host material of the assemblies. Now, a coiled pin in general would be the best option, best fastener for that, and then it would just depend on the application itself, deciding between the different duties that we have, which would depend on the magnitude of those vibrations. So generally speaking, all of them would be great, but we would need to evaluate based on the exact requirements. Well, thank you everyone for attending. This was a great webinar for us.
Yes,
great questions.
Great questions from everybody. We really appreciate your time today and spending that with us. If there's anything that you ever need, please reach out to us. We'd be more than happy to help.
Thank you, everyone, and have a great day.